This week's Tech Talk is about reinforcement learning. So this was a new topic for me as well, since I'm not a researcher or anything. First of all, this is regarding machine learning. The broader area is machine learning. So this is actually a subtopic on machine learning. So this presentation is all about getting at least some of you interested, because this is not a topic that we have encountered even when hearing cool things that has been happening in the technological landscape, because we most of the time we talk about machine learning, data processing, big data, natural language processing, making business predictions, voice assistance, autonomous driving. We hear all those terms, but this was not a term that I had heard about some time back. I don't know about you. Have you encountered this term? Like, no, right? So I hope not. So so then that means I'm the master regarding this topic in this room, even though I also know next to nothing. So again, so this is about machine learning, the subtopic of machine learning. So the word reinforcement in an English sense, it means kind of repetitive. Just mean it as a repetitive learning. Okay. So before moving on to this one, so let's first look at machine learning in general. Try this. Oh, I have to plug this in. Yeah. So machine learning in general. So I'm pretty sure you have heard a lot about machine learning. Even related to our own engineering disciplines, I think we have had presentations regarding Azure machine learning, big data, Microsoft Power BI, business analytics, predictions, and all sorts of things. So I hope the dongle is not lost. Oh, it's here. It's here, right? Yeah. I hope Perera doesn't look. Can someone? Ah, it's here. It was inside. Sorry. So I just want to get your attention to a couple of big events that we have heard about in our lifetime, probably when we were young, when we were going to school. Hands up those who remember this. Hands up. Okay, some people do remember. So this was in 1996. At that time, we knew it as a computer named Deep Blue has defeated the chess champion at that time named Garry Kasparov. So this was kind of, this made waves around the world, a computer beating a human best player in a game. So I think it's kind of fitting today, because yesterday we had a chess exercise and I heard people talking about it on the lunch table as well. So this was regarding chess, a computer algorithm or a software learning to play chess. And then recently, I'll give you, I heard this, so the computer named IBM Watson again won in a game called Jeopardy, which again is very human game. More than chess, it has more to do with human intuition, language, natural language processing, and thinking. In this game also, IBM Watson came on top, and after that, now IBM has an entire suite of machine learning and AI services under the name of Watson. And then very recently, Google's DeepMind, Google subsidiary DeepMind, came up with software called AlphaGo, again to play not chess, but this time it was a game called Go. It's an ancient Chinese game. So the difficulty level of this game, the board game, is like multiple orders of magnitudes than chess. But still now it's 2016. Now this latest artificial intelligence software or machine learning software has been able to learn how to play Go and beat the world champion. So I'll just take this last example in bit more detail. So let's just see so one point of this presentation is I want to find out how the hell this learning happens. We talk about machine learning, but we don't know how it learns. Where is that memory is kept? I mean, when we are thinking about ourselves, we sort of have the intuition that our memories are kept in the brain and we learn from our experience and so on. But in machine sense, the learning process happens. But since we are not researchers, it's kind of difficult for us to understand what the concepts that's involved. So since I'm also not a researcher, this is kind of an attempt for people like us to understand how machines learn. So in this particular example, Google's AlphaGo software beat the world champion Isidore, the Go player. So you can see the Go is a very much simpler board, simpler rules than chess, but its difficulty level is much higher than chess. So there are just white and black stones, and whoever has the most colored stone, if you are white, you have most number of whites on the board, you win. So more than chess, this also revolves around human intuition because the possibilities are too much. Unlike chess, there's very little chance you can get logical advantage out of many situations. So this is much older than chess as well, like older than 3,000 years. So it's a big. I recently talks about this. There's a big culture in Chinese and Korean countries around this game of Go. It's a different culture actually, like a religion. So to win this AlphaGo software did not calculate all the possibilities and calculate the best possible outcome, because the current computing power the world has is not enough to calculate all the possibilities and come up with the best decisions. Because computers are usually good at that, right? If you have a lot of things, you can just very fast manner you can process all the possibilities and take the best decision, unlike us. But these kinds of games put computers and humans on equal grounds. I mean, unless we have a new technology like quantum computing or DNA computing or something like that, maybe that's a good topic for lightning talk if anyone is interested. The current silicon-based CPU technologies is nowhere near enough to calculate the possibilities of this game. And actually, it's been estimated that all the possible board configurations and the movement possibilities, the number of possibilities is much higher than the total number of atoms in the universe. Just think about it. Total number of atoms in the universe, in the entire observable universe. In fact, in chess also it's much bigger than that atoms number. But here it's much like unimaginably bigger than the chess game as well. So it just cannot rely on brute force, all analysis and taking the best decision. And another thing is, unlike the Deep Blue software which played chess, this software did not actually know how to play this game. But it somehow played it, but no one had taught it. Other than the very basic rules, basic set of rules, these are the strategies you have to use. In this kind of a situation, you should take this kind of a path to maximize your chances to win. In chess, obviously, as we played chess, you would understand that in certain situations there are certain strategies you have to take. In this game, there are strategies like that, but the software algorithm didn't know about any of those things. So it completely learned just by observing thousands upon thousands of human games, which has been played throughout the history, any recorded games. Again, it is like learning from big data again. So it just learned by simply observing the games that's already being played by humans, but by watching it over and over again, the software has become better than humans. So that's the story of so we'll come back to this again at a later stage, but just remember this AlphaGo software. Now let's talk about little by little getting into big theoretical stuff. Difference between programming and learning. We understand this very well, right? Programming is a predefined workflow to calculate the answer. Like you draw flow charts, pseudocode. You can basically for every it's mentioned. So for every input there is a defined output. If the output is not there, then that's a bug. So we try to correct it and try to fit to the original predefined workflow. So we all understand. But learning is fundamentally different from that. It's all about, maybe it's even difficult to define as well, but it's all about trying to adapt to different situations, maybe from what you already know, or even if you don't know about it, learning means getting to know about it. So in learning, it's very difficult to define all the possible inputs and outcomes. So if we were a computer program, how many inputs and outputs we would have? Like if you meet a person, if he says this thing, you should respond in this way. If he says a slightly different thing, you should respond in this way. It's impossible, right? But throughout from our birth, we have learned how to interact with people, we can't define it, but somehow we have learned. So that's the difference between programming and learning. So it's just figuring things out. The problem domain, the inputs and outputs, we can't define. And so let's get into machine learning. So we use our brain for our learning, right? So obviously our eyes and our fingers could be the inputs, but the actual learning happens in the brain. So in terms of machines, the tool used for learning is neural networks. I can't say actually that the tool, maybe it might be the most popular tool. There are a lot of other ways of learning as well, but the term we have heard about is neural networks. The reason we have heard about it is because it's the most popular tool. It's popular in our industry, it's popular in the research projects. So that's a tool. So let's talk a bit about neural networks. Because if you haven't followed any neural networks courses in the university, neural networks attempt to simulate the behavior of our actual brain neurons. So we do this all the time, right? The airplanes try to simulate the behavior of the wings of birds. Like we take some natural phenomena and try to adapt into our artificial tooling. So this is also the same story. And you train your neural network just like our brain by repetitive stimulation. The more and more inputs we get again and again, our brain gets tuned to that particular scenario. Right? If this was the first time you are exposed to, let's say, programming, you would suck at it. Right? The more and more we program, we write code, our brain works better and better when we are writing code. So that's repetitive simulation. And in another way, neural network can be taken as a mathematical formula to closely approximate brain function. So even in the brain, when you give some sensory input, something happens, right? There is some outcome. Maybe when I see Salun, maybe I want to hit him in the face, right? Actually not, I don't feel that way. But that's my brain's outcome. So that might be the same thing done by neural networks in terms of machinery learning for a given input. This might be the next outcome. But there's a flip side of it. So when I hit someone in the face, he might hit me back. I might fall on the ground. So then that would add to my learning experience not to hit someone again. Okay, I get schooled. So again, these outputs might in turn generate more inputs. And that could also help me learn as well. So neural networks has all those concepts built in. So this is just an image of brain neurons. I don't know whether this is a real image or not. It just looks like it, right? It's a very complex, huge network. So you have these are the neurons, and these are, you learn these things in the science class, right? Axis, accelerator, some various terms. So there are connections, there are neurons. So one neuron might be connected to a lot of other neurons. So it's a huge network. So artificial neural network is also like that. You have a lot of neurons and a lot of connections. And in this diagram, these are the input neurons, these are the output neurons. Maybe this is like eyes, and these might be your fingers. You see an object, you want to hold it. So the output goes to the fingers. So something like that. Right. So this is very boring stuff. Okay? But just bear with me. It's only for a few slides. Because I thought these are like must know things to know about neural network. This is a very simplest case. A mathematical model of the neural network is you have the neuron, you have let's say 3 inputs in this example, and 1 output. So I told you we are trying to get a mathematical formula to simulate the brain function. Right? So this is a simple mathematical formula. Right? Not very difficult. Y equals this x, wx, just a summation. So this is the formula used in all the neural networks. So let's, in our traditional terms also, x usually stands for inputs, y stands for the output, right? So let's find out what these W values are. These are actually called weights, and they represent the connections. They actually represent the strengths of the connections. If I go back to the earlier image, in biological science, said that it's not 100% correct, but if you are being trained on something, those connections to those activated neurons get stronger and stronger. Let's say due to an accident you stop using your hand, then it's very highly probable that the neurons that connects the hand to the brain might get weaker and weaker. So even after the wound gets okay, now you cannot move your hand because the connections have weakened. So the strength of the connections also matter. So these weight values are kind of an attempt to simulate the strength of the connections. So again, we go back to the science class. Just try to remember whether you did something like this in school. You did an experiment, let's say measuring the temperature of some object over time. And you apply it and you measure the temperature over time. Have you done this? Drawn the data points. Then what did you do? You tried to draw a line to represent all the data points. So what's the purpose of drawing this line? Anyone? Just asking a question so you don't fall asleep. There's the exact relation between these data points, right? extrapolation. So we only know about these 1, 2, 3, 4, 5 data points, but we are trying to predict. So when the time is this was the temperature. But using known data, we are trying to also calculate unknown data as well. So that's why we are trying to draw this line using this small curve fitting. And we also used a very familiar formula like this, right? Y equals mx plus c. And y, x is the input, y is the answer. And these m and c values, it depends on the line you draw, right? Depends on the line you draw. So if you change the line, these change. So basically, these values are used to tune the line, right? The better tuned these values are, the better your formula is in predicting the unknown data. If you draw shitty line like the data points are here, let's say you draw a line like this, then these values are getting different. But this formula is going to do a lousy job at predicting unknown values, right? So the main goal of this is to find the best possible values for these constants. So I'm going to get, I don't know the distance. So these values. So it's the same thing, same kind of tuning that's happening in these W values as well. Just like we had known data points in that science class, we first give known inputs and we know all the outputs for those known inputs. And we try to give more and more known inputs like that, and we tune these W values. Then after that, we get that formula, just like we use y equals mx plus c to predict unknown values, then we just keep using this formula. That's it. That's the basis of a neural network. After you tune the formula, you can use it as is. Then after that, there's no more tuning. So this tuning process is actually the learning process in neural networks. So you get it to learn by feeding more and more known data in this example. So this is just a very simple example. Okay. So let's say you want to design an algorithm to detect flowers, right? One of most, I think we might be able to do these things in Azure machine learning as well. You feed. As a human, you know all these things are flowers. And you prepare a very big data set containing a lot of flower pictures. And you know for all of these pictures, the answer should be, it's a flower, right? So you try to feed all these known inputs into the neural network and tell it to tune these W values. So for every picture, Y would return true. Y would return it's a flower. So the more and more pictures you give it, it will give you W values. So basically, this is not a neural network which is capable of doing that. We will use just one neuron. I have just drawn this for simplicity. I will draw it. I was too lazy to draw something. Just found it on the internet. So that's the training process. So in fact, this is called supervised learning. So we'll get to that in a bit. So after you train it, then you can give an unknown image and ask it, is this a flower? Then it will just do a simple mathematical calculation using the tuned W values and give you the answer, true or false. That's it. Okay. You guys got that, right? So there's no one structure of neural network which can learn anything. One size does not fit all. So in fact, there are a lot of variants of neural network models. I don't know about them. There are many people who did neural networks in the university who remember some stuff. Convolution, feed forward, neural network, a lot of fancy names. Time to time, people come up with new models, new structures to fit new problems. And people maybe pick one slightly modify an existing one to solve this problem. Have you heard the term deep learning? Deep learning. In the internet you find that deep learning means something like this. So if in that learning process, the neural network used is very deep. We call it deep learning. So in this case you can see there are a lot of layers between the inputs and outputs. So input has to travel through a lot of neurons to reach the output. So these are called hidden layers. If you have number of hidden layers, they call it deep. It's a deep neural network. So most of the learning algorithms nowadays we employ deep neural networks, so people call it deep learning. So this model, having different models for different problems, is exactly like this. Now again going back to the science class, just imagine the data point set like this. And we try to apply our old thinking and just try to apply this, because this is what we know. We try to apply that thing for all the problems we have. Let's say we draw a line using this y equals mx plus c. So obviously this doesn't fit. No matter how much we try to adjust that line, we can do a better job. So maybe this is a very simplistic example. The line or the curve to represent these data points might be something like that, not a straight line. So the formula would change, the structure of the formula would change, right? So this is finding the best formula for your problem. So a researcher has to do that when he wants to solve a problem. He also has to choose the best neural network structure to better solve this problem. That's that. And so there's a nice tool by Google called TensorFlow. Using this, you can actually learn about neural networks as well. For me, it was just something to play with, because I don't know the concepts of neural networks. Maybe if you are interested, you can play around with it. Anybody who have used this have seen it? You have used it? Priyadarshan, have you? So this just gives you sample data sets, because the main purpose of this nice JavaScript application is to get you to learn neural networks. So it's like a classic classification problem. So you have two colored dots. The problem is, how do you come up with the formula to separate out the two colored dots, right? So let's take the simplest one. So you can think of a number of ways, right? Just draw a simple line, like just like the y equals mx plus c, just draw a simple straight line, it will divide the two colors. But a problem like this is much harder, right? Like you have to draw a very complex curvy line, and just imagine how complex that formula would be to draw that curvy line. So let's take that simplest one. So this is, you can visually design your neural network. I'm just doing monkey business here, okay? I think it works for one neuron as well, because so you can see it quickly learns, it quickly tunes its weight values, so it comes up with the final values to cleanly separate them. So you can see this connection weight, final weight values it has come up with. So ultimately this should just give you a mathematical formula, and that mathematical formula is represented by this line. Okay? So let's do this. You can feel it's a bit more difficult, but let's just reuse the same model as previous. Again, it tries to draw a line, but it will never be able to divide it, right, with a straight line. You actually need kind of a circle in the middle. So to draw a line, y equals mx plus c is enough. But to draw a circle, do you remember the formula for the circle? Like, much more variables are involved, right? I don't remember, like you have x squared plus y squared, like bit lengthy formula for a circle. Just like that, you need more neurons, or you need more layers of neurons. So let's just no, let's add one, or say just for fun, just let's add three neurons. Now you can see it's sort of mimicking a circular curve, and learns, okay, this is fitting. Maybe by increasing more things, you can get a smoother, more circular lines. And you can also say increase the layers. I don't know the effect of it. You can see the learning process gets different when you have more and more layers, and the way it learns, way it tunes is different. So you can have fun with it if you want. Maybe you can find out how to model the neural network to separate this out. Uh, if you have domain knowledge, if you have academic knowledge, it is straightforward. So this is TensorFlow, and it's just a test page. It's actually a library for neural network programmers to use. I haven't used it because it's not my area, but for researchers, this might be a very useful library. TensorFlow. Okay, so that's that. Um, then we get out of neural networks and come to the next step. So all this time, all this half an hour, I talked about the tool used for machine learning, which is neural networks. But this same tool can be used in different ways. Okay? Just like the hammer, you can use it to put nails into the thing or pull the nails out. So the same tool, there are different ways you can use to learn each machine. So the first one is supervised learning. Supervised learning, you saw an example with the flowers. So it's like you have a known set of questions and answers. So by those known things, you train the neural network, and then you ask it some unknown thing. Right? We mostly get these things for brain teasers. Right? The first things are this, what's this? So that's supervised learning, because there is a supervisor who is giving. Okay, these are the examples. These are the known things. What is the next thing? And unsupervised learning, again, you have to give it data, but you don't have to give it answers. Right? It is like you input all the sales figures for the past year, and then tell it, figure out who are the best customers, who are the most loyal customers out of that data. Right? You do not have to guide it through. Okay? This customer is good, this customer is bad, this customer is not that good. You do not have to guide it in unsupervised learning. You just have to give it data. But common thing in both these approaches is you have to give it data. You have to give it a lot of data. The more data you give it, the better tuned the weight values will be. The better tuned your algorithm will be. So now we come to today's presentation topic. After half an hour. So this is the third one, reinforcement learning. In fact, these two are the most popular things in the world up to now. Maybe up until a few years ago, these were the most popular. But nowadays, maybe from a couple of years back, this is now becoming very popular, and it's very cool as well. So I'll show you some cool videos as well. Maybe the people who are sleeping will wake up. This like boring stuff. So reinforcement learning is all about just keep trying until you get better at it. Okay? It's like now this is like learning in school, right? Teacher gives us instruction. These are your first few examples, and then the exam paper you get the very complex question to answer from your existing knowledge. But reinforcement learning is more like a child learning. Like no one gives instructions to the child. So if you want to walk, you have to take the step like this and then take the other step. You don't give instructions. There's no supervisor. The child just falls to the ground, he learns himself. Just keep trying until you get better at it. So this actually mimics the human or how any creature would learn from scratch, from zero. So just to uh, get you lightened up, there are two examples: reinforcement learning algorithms learning to play games. I can't find it.
Mixes together these two concepts and we call it deep Q learning, and it is able to learn to play games the same way as a human would. It is not exposed to any additional information in the code, all it sees is the screen and the current score. When it starts learning to play an old game, Atari Breakout, at first the algorithm loses all of its lives without any signs of intelligent action.
So this is, unless in case you get confused, so this is like the video has lot of gameplay sessions, one after the other. So you can look at the score here. I think. So when the ball goes here, it starts a new one immediately. So it goes very fast. Just watch over the score. So you can see it's never able to get beyond one score.
Atari
Right?
Breakout,
It's
at
like
first,
we trying to play Flappy Bird for the first time, right? You can never get past
the algorithm. If we wait a bit, it becomes better at playing the game, roughly matching the skill level of an adept player. But here's the catch: if we wait for longer, we get something absolutely spectacular. It finds out that the best way to win the game is digging a tunnel through the bricks and hit them from behind. I really didn't know this, and this is an incredible moment. I can use my computer, this box next to me, that is able to create new knowledge, find out new things I haven't known before. This is completely absurd. Science fiction is not the future. It is already here.
So
it also plays many other games.
yeah, you can see it has improved a lot after 240 minutes. Minutes, right? 40 minutes, a few hours. Uh, how can it do that? I mean, does it know how to play this game? Does it know that this is a ball? I should protect the ball with the bat and not let it go beyond that? Actually, it doesn't. So you can see in the very first slide we mentioned all the knowledge that this algorithm is given is the computer screen. So the algorithm just receives the pixel color stream, and maybe it could also receive a separate coding, manual coding, to decode this area, to decode the scope. So it will just keep doing random things until the scope is increased. Okay? So if the score stays 0, it could think, maybe what I did earlier was not good enough. Maybe let me try a different thing next time. So it will try so many, maybe millions of stupid things, but eventually it will get better at it. So, and all it knows is there is some controller, left or right. So he will press left or right. He doesn't know when you press right, this goes here and it will protect the ball. He doesn't have that knowledge. But it just remembers the patterns it tried, like left, so left, right combinations and all that. But it also doesn't remember everything. So, do we remember all the human faces that we have met throughout our lifetime? No. But when I see here, I can recognize him, right? But I don't, if I had to draw his face, I wouldn't know how to do that. But I just know it. Just like that, throughout the learning experience, this algorithm's neural network gets trained. And it can use that trained neural network to play the game very well. So there's another one. Again another game. So the good thing with games is you can because there are no physical constraints, you can play it millions of times until you get better. Even though you are very stupid, you can see it's just doing random things. Maybe it's pressing to the right too much. So after a while, it just tries different things. Still, it gets killed. But at the end, he just surpasses human level play. So because there's just constant progress very fast. Okay? These are some cool applications. Um, so let's talk about the differences between how machines use reinforcement learning and how living beings, us, use reinforcement learning. Okay? You would recognize this picture, right? Do you recognize a person? Right. Good. So you can still recognize even with the blindfold. So I took this example because it's very hard for us to imagine we doing reinforcement learning because we are always doing supervised learning. When before we learn the programming language, we follow a tutorial and already pre-learn the concepts and then get into programming. We don't try random keywords, random English letters and try to see whether the program compiles. Right? We don't do that. We actually don't do reinforcement learning after our infant ages. So maybe this would be a good example because you are just going blind. Uh, so you actually have to imagine learning something blind. Now, here you are not making intelligent decisions, right? Because you do not have information, you are just rotated and then told, okay, now go, and then you just randomly go, right? Of course, others help, that's again supervised learning. So others help, like, hey, don't go there, go this way. So what you should really do is just randomly go and try to just put the eye. Maybe the board is there, right? Then it would be a very little learning experience for you. Maybe next time you would try to change your strategy a bit. Still, you would be off point. But if you just imagine, if you were training to be a ninja of elephant game, you would train day in and day out like, for weeks and weeks. You would actually get better at it, right? No one will be able to beat you in every out of the festival. You would win the game, right? Because the more you do it, the more trained you are in your strategy in reaching the eye, right? That's reinforcement learning for you, right? But to become better at it, you would have to spend at least days. Same thing with machines. They also learn blindly. And it's not making intelligent decisions. But the key thing is repetition. Okay? Same as us. And repeatedly makes it better. Same thing, right? But what's the difference then? How come these machines come on top of us? How do they get better than us? So these are the reasons. They can repeat super fast, right? Millions of times faster than us. The same zone. Because they are unknown silicon, they are fast. And they are not bound by physical limits. So we get tired. I mean, there's only so much we can do straight away. Here you can just let the algorithm repeatedly run and just get the final result. And the main thing is it does not forget what it learns. Right? If we just keep out of touch for a few days, maybe we will lose touch. That's why professional players they train every day. They can't go to nightclubs and do crazy things. In like just like the cricket team, they will get worse. So this is the power, right? But conceptually, it's actually very dumb. Like just imagine my example was blindfolded learning. It is very dumb, right? But doing dumb things very fast, you can get superhuman. So that's the whole concept of reinforcement learning. So I found a cool application, I think written by a neural network keyword researcher. It's a .NET application, and I think he does pretty good .NET as well. He knows good software design concepts as well. Their source code is also available. I didn't look at the source code, but I just want to show you the app and one of the experiments. So he has a lot of experiments. The only thing that made sense to me was this half cheetah experiment. So this is like a machine trying to walk. So he has an artificial cheetah-like skeleton structure. So it has to learn to walk itself without using any knowledge, basically, right? And there are different agents. So this actor critic is a concept used in reinforcement learning, like based on your outcome, like just like the elephant game. After you put the eye, then only others will tell you whether you are warm or cold. Like, are you closer or are you further? Like, using that, you adapt your next strategy. So just the actor critic agent. Basically, it criticizes your outcome. Okay, so let's just do this. So you can see it's just a skeleton structure of creature. It looks like a creature to us, but for the machine, for the algorithm, it's just a set of joints. And all it knows is it can move these joints. It doesn't know the concept of walking as well. It doesn't know these are legs. Who says these are legs? Again, we are telling these are legs using our preconceived notions of animals in the world, right? The goal of this algorithm is to get this structure from here to like maximize the distance, basically, maximize the scope. That's all it knows. So what it does is it just randomly tries to move its muscles, move its joints, and just see whether it goes somewhere. Right? I'm not sure whether you can see this. So you can see steps in current episode, and there are episodes 6 out of 2000. So now it's 7 out of 2000. An episode is like one session, just like that elephant game. You put the blindfold and put the eye. That's one session, one try. Okay? Based on the outcome of that try, you try to optimize the next try. And this algorithm, you can configure this. You can you just see running it for 2000 times and see. Okay? Now we wait. No, I'm not going to do that. So now you can see. You can see in the first few sessions, it didn't even do that, right? It was staying in the same place, but now it has progressed a little. So this algorithm is actually very slow when it has to update the screen. So there's this background learning functionality as well. So you can see the number of episodes quickly increases. So just run it. So just undo this. So that's how it learns. So you get the idea, right? So at one point I ran it up to 2000. Somehow it has find. I mean, probably towards this kind of stage, maybe it has learned to move the legs and it took this going like this. But when it reaches around here, it falls down. But it has learned to walk that distance. Just imagine an artificial creature learning to walk, just like in nature. Okay. So now it has gone beyond the earlier position. Definitely. This is progress. For us, it might not be progress, but for the pure goal, it's progress. So surely its neural network might have been trained a little bit towards that direction. So that's that. No, not brute force. Not all the possible combinations. Maybe in the first few things, it might do a random movement. Just do random movement and see where I go. And if it achieves better results, maybe just keep doing. Just there are variance factors as well. Just apply the variance factors in that direction, so you can keep improving. This is not brute force. Maybe in the beginning there is a random component involved as well. So different learning sessions might even achieve different results. So if it was brute force, you would always get the same best result. But here there is a risk as well. You going down a non-optimal path, whereas you think that might be the best path. Like that. We call that local minima versus global minimum problem. So that's that. It's not brute force. Huh? Yeah. No, it's like for this experiment, this guy have count this. You can put the values for this guy. So let's say for that early Atari game, that breaking the bricks game. I don't know how many episodes that they use. Like they just tell 240 minutes. Maybe it's millions of episodes to reach that level. Maybe even this program, if we run it for million episodes, maybe we might get very fantastic results, or we might even be stuck in the same position. We just don't know. Even the creator himself couldn't know. The programmer himself couldn't know. That's one of the beauty of it, not knowing what's the outcome. Oops. I had work. So this is another video. This is another walking experiment, much more sophisticated.
No. And the selling point of this new one, which you might say looks less elaborate. However, it synthesizes them from scratch. The problem is typically solved via reinforcement learning, which is a technique that comes up with a series of decisions to maximize a prescribed score. This score typically needs to be something reasonably complex, otherwise the algorithm is given too much freedom to maximize it. For instance, we may want to teach a digital character to run or jump hurdles, but it may start crawling instead, which is still completely fine if our objective is too simple. For instance, just maximizing the distance from the starting point. To alleviate this, we typically resort to reward engineering, which means that we add additional terms to this reward function to regularize the behavior of these creatures. For instance, we can specify that throughout these motions, the body has to remain upright, which likely favors locomotion type solutions. However, one of the main advantages of machine learning is that we can reuse our solutions for a large set of problems. If we have to specialize our algorithm for all terrain...
So why do you think that he's waving his hand? Where is it? It doesn't achieve anything, right? But maybe that's how it learned. Maybe that's, I told you, it's just doing some random things initially. Maybe the initial random path it took involved waving of the hand as well. But at the same time, he was moving his legs as well. So he sticked with that pattern. So it doesn't know the natural motion. It doesn't know the difference between natural motion. Those are all concepts of us humans. But all it knows is increasing distance from the starting point. And whatever it does, in order to achieve that, no problem with that.
And motion types and different kinds of games, we lose out on the biggest advantage of learning techniques. So researchers at DeepMind decided that they are going to solve this problem with a reward function which is nothing else but forward progress. That's it. The further we get, the higher score we obtain. This is amazing because it doesn't require any specialized reward function, but at the same time there are a ton of different solutions that get us far in these terrains. And as you see here, beyond bipeds, a bunch of different agent types are supported. The key factors to make this happen is to apply two modifications to the original reinforcement learning algorithm. One makes the learning process more robust and less dependent on what parameters we choose, and the other one makes it more scalable, which means that it is able to efficiently deal with larger problems. Furthermore, the training process itself happens on a rich, carefully product of this kind of problem formulation body when is like means that we most likely doesn't probably choose with a sped up remix video with some Benny Hill music. In summary, no pre-computed motion database, no handcrafting of rewards, and no additional wizardry needed. Everything is learned from scratch with a few small modifications to the reinforcement learning algorithm. Highly remarkable work. If you've enjoyed this episode and would like to help us and support the series, have a look at our Patreon.
That last one might be a properly trained outcome of the research. So there's another one. Remember I talked about AlphaGo in the first slide, the algorithm which plays Go, and I told you that software learned it by observing thousands and thousands of games. But now there's a better version, AlphaGo 0. So I actually have Amulet to thank for this. He found it out and sent to me. So AlphaGo 0 is a reinforcement learning agent which learns AlphaGo from scratch without any human game inputs. So that's a crazy thing. It just learns to play with itself for millions of times, and now it has beaten that previous AlphaGo which beat the world champion as well. Just no human input, no human research, no human games, anything. It has learned for itself. Crazy.
AlphaGo has been through many generations now. The first generation of AlphaGo, which we published in our original Nature paper, was able to beat a professional player for the first time. Now we have the final version of AlphaGo, AlphaGo 0, which has learned completely from scratch, from first principles, without using any human data, and has achieved the highest level of performance overall. The most important idea in AlphaGo 0 is that it learns completely tabula rasa. That means it starts completely from a blank slate and figures out for itself only from self-play and without any human knowledge, without any human data, without any human examples or features or intervention from humans. It discovers how to play the game of Go completely from first principles. So tabula rasa learning is extremely important to our goals and ambitions at DeepMind. And the reason is that if you can achieve tabula rasa learning, you really have an agent that can be transplanted from the game of Go to any other domain. You untie yourself from the specifics of the domain you're in and you come up with an algorithm which is so general that it can be applied anywhere. For us, the idea of AlphaGo is not to go out and defeat humans, but actually to discover what it means to do science and for a program to be able to learn for itself what knowledge is. So what we started to see was that AlphaGo 0 not only rediscovered the common patterns and openings that humans tend to play, these Joseki patterns that humans play in the corners, it also learned them, discovered them, and ultimately discarded them in preference for its own variants, which humans don't even know about or play at the moment. And so we can say that really what's happened is that in a short space of time, AlphaGo 0 has understood all of the Go knowledge that has been accumulated by humans over thousands of years of playing, and it's analyzed it and it's started to look at it and discover much of this knowledge for itself. And sometimes it's chosen to actually go beyond that and come up with something which the humans hadn't even discovered in this time period, and developed new pieces of knowledge which were creative and novel in many ways. We're all really excited by how far AlphaGo 0 has come, but I think what we're most excited about is how far it can go in the real world. That the fact that we've seen a program can achieve a very high level of performance in a domain as complicated and challenging as Go should mean that now we can start to tackle some of the most challenging and impactful problems for humanity.
I'm not sure whether you got that. He mentioned that now Go is like around 3,000-year-old game. So obviously there has been certain concepts, certain strategies, certain smart moves, tips and tricks that have been mastered across 3,000 years by the Asian civilizations. But this AlphaGo 0 has learned for itself all of that within the number of hours that it's been trained, and even going beyond that, discovering new strategies to outsmart 3,000 years of worth of human knowledge. So that's crazy. So this is the learning curve of AlphaGo 0. So it starts from, I'll tell you what this zero rating is. So after 3 days, features the level of previous AlphaGo version. This is the level and master level. Yeah. Yes. It has been a second version as well. Now it has gone here as well. So this is the level of 3000 years of human knowledge. If we consider the world champion Lee Sedol as the pinnacle of the Go game, Go strategies, is that level. So just in 3 days of constant learning with this set, that's a crazy thing, with no external input. It has smart and it's still improving. A bit slowly, but it's still improving. And this ELO rating is a rating used in games like chess and Go, like basically one-on-one games, as a standard rating of players. Just like the IQ score of a person, these are rating for players for games like chess. So that's AlphaGo 0. So I would like to, we are towards the end. So do you remember Dijkstra? Dijkstra's shortest path algorithm. So he has said the question of whether machines can think is about that, and then as a question of whether submarines can swim. So we in the science fictions, and when we talk about machine learning, we always talk about artificial intelligence. When will machines be able to think? But maybe that's not relevant. As long as it can do the things very much better than us, whether or not it can think, it's just like asking whether submarines can swim. Submarines can swim much better than fish, but it's not swimming, right? It's just a machine with a propeller. It just achieves the same thing with a different tool. And then there are some issues as well. Not only the positive side, there are some shortcomings as well. Main thing is multi-purpose training. Now I told you these neural networks and everything is trying to mimic human brain function, right? When you look at things like AlphaGo 0, you would think that, oh my god, it's actually surpassing what humans can think, come up with new strategies. But the catch is, if you train the same AlphaGo 0 neural network, if you take AlphaGo 0 and start learning about a different thing, let's say riding a bicycle. It could suck at riding a bicycle at first, but we could get better, but it could start to suck more and more in Go, right? Because it's just one neural network. So one of the unique things in human brain and the living brain, animal brain, is like you can learn so many things without compromising anything. When you learn to drive a vehicle, you don't forget how to ride a bicycle, right? So that's the power of the human brain. So still, humans haven't figured out how to apply that into artificial learning, artificial neural networks. Maybe that's way to the future. And the next thing is unpredictable. Even the creator of that algorithm, creator of the artificial neural network, might not know how it would be trained. What would be the final trained tuned values? And based on the tuned values only it functions, right? If you don't understand, if you cannot foresee the tuned values, you don't know how it will function. So I think recently the Facebook guys came up with that two bots to teach, try to learn and talk to each other, and suddenly I think maybe it might also have been a reinforcement learning experiment. So by repetitive learning, maybe they have invented their own language to communicate. So it wasn't something that researchers had anticipated as well. That's unpredictable. And applicable domains are not that clear. So this is mostly specific for reinforcement learning. Now, reinforcement learning is not that good in big data problems. Big data problems, you either need supervised learning or unsupervised learning. Reinforcement learning is actually all about learning from scratch. You cannot use it to figure out the loyal customers of the past year. Right? Maybe that might be one of the reasons it hasn't been popularized in the industry, because all the money is with this business analytics and data analysis and all of those things. But it is very useful for things you can do repetitively, specifically learning games. Or there might be some other domains that people are now pursuing. It is fairly recent, that interest. That's that. Okay, so those are the issues, and I think we have come to the end of the presentation. Sorry, the talk. So this is that .rl app I showed you. There's a research paper on that as well. So he has done that research paper to introduce this as a platform where researchers can use this to learn neural networks. So the source code is there. And 2-minute papers is a YouTube channel that I showed you videos from. It contains a lot of research paper videos, but that particular guy who does that, he's also most interested in machine learning. So you can find a lot of 2-minute summaries on research papers. Pretty cool. There are nice experiments he shows visually, like lip syncing, voice synthesis, and all of that. Very cool example. And this is a talk I watched from the Google DeepMind CEO, who designed the AlphaGo program. Someone called, this was a talk from when AlphaGo beat 2016 World Champion. He talks about Go, like very interesting stories about Go, the Chinese culture, and everything. In fact, an interesting fact is, he mentions in Go, just to tell you how serious it is, if in China or Korean countries, if a child is, let's say, a 4 or 5-year-old child, if he seems to be gifted that Go, they are taken out of the school, and like from the childhood they are trained in Go schools, like completely. Just like in movies like Shaolin temples, the child monks train in the Shaolin temple, so they learn Go day in and day out, like 24/7. So that's how big the Go culture is. So there are a lot of stories in that talk. Yeah, that's it. Okay, I hope you learned something from it. If you have any questions, you can ask, but just not like I have more knowledge than you, but we can discuss. Like 5 minutes past the time slot. Okay, thanks for asking questions. Thanks for listening.